Somebody told my wife that this was the most difficult material that we had all year long. You think so? Listen, stick to that homework. Make sure you're looking at the homework now. It's a lot like stuff that we've been doing in class, but start doing that homework right now. Your exams, I'm going to go through your homework. I'm going to pull your exams a lot from your homework, and then also look at the examples that you do in class. Okay? So look at the homework, look at the examples you do in class, and then, the concept test. You'll have a few multiple choice questions. Okay, so if you do that, you'll be okay. We are going to do that differential equation thing, and I'll probably give it to you today, but we're going to do that as a take-home. One of the students suggested that we do it as a take-home. So, what?
What?
So you can thank them, those students. That's all right. Right.
Yes, that's all right.
That was a good idea. So you're not solving the differential equation. You're just showing that the solution works. It's just doing derivatives. I just want you to work with it a little bit and just show that it works. But it'll be a little more complicated than what we did before. We're going to do it for a damped oscillator. A lot of what we're doing here will be useful for what you do, say, in P-Chem when you look at different types of decay things, the way you deal with them mathematically. So you're probably not going to see LC circuits or LRC circuits again, unless you're double E or go into graduate school and do some of your own instrumentation. But the mathematical stuff will come back. We're going to look at inductor capacitor circuits, LC circuits. Remember last time we looked at LR circuits, and LR circuits are basically exactly like RC circuits. You work with them exactly the same way. The curves look exactly the same. The equations are basically the same, except for a little bit of mucking around with the time constant. You have all those equations, but they're exactly like RC circuits. We did RC circuits already, so hopefully you can transfer what you did there over to C in the LR circuits. They work mathematically exactly the same. The reasoning is a little bit different behind them, but they work exactly the same. LC oscillations, on the other hand, we haven't really seen anything like this before. An LC circuit has a capacitor, right? That's our C, and then it also has an inductor. That's our L. And in LC circuits, our charge, our current, and our voltage are all going to vary, and they're all going to vary sinusoidally. All right, so remember our capacitor has a certain charge on it. There will be a current through this, and then we'll also look at the voltage of the capacitor as well. And those are all going to vary sinusoidally, because as you send a current through the inductor, as your current increases, your inductor is going to oppose that current. As your current decreases, the inductor will go in the same direction as that current. Remember, the inductor wants everything to stay the same. So whatever it's doing, it's going to be opposing that change. We saw that already in the LR circuits. We've already gotten the energy of the capacitor and the inductor, and that'll come up here. The energy of the capacitor, this was from chapter 4, I think. From chapter 4, the energy of the capacitor is given by U equals to 1/2 Q squared over C. That's just our energy of our capacitor. That's on your equation sheet. It is, let's go to that equation sheet. It's not under this chapter, it's under chapter 4, I think. Where is it? Yeah, here it is, under chapter 3 actually. There's our energy of a capacitor. Now listen, the energy that's stored in the capacitor is due to an electric field, so we'll call this UE. Let me put that in writing. So the energy stored in the capacitor is due to the electric field. So when I write that energy, I'll write it with a subscript E. But just remember that's due to the electric field, because when I have that capacitor, it's two metal plates with charges. There is then an electric field that's set up between those two electric plates. And in that electric field, there is a certain amount of energy. and that energy is given by the charge and the capacitance in this way. And then also, we've already found the energy of the inductor. It's equal to 1/2 Li squared. The more current I have, the more energy I have. And the inductor, if this is due to an electric field, what is this due to? The inductor, the energy. What do we have in an inductor that contains energy? A magnetic field, right? So remember, with our inductor, when we have a current that is changing, when I have a current going through this, I have a magnetic field. And in that magnetic field then is energy. So because this is due to the magnetic field, I'll call this UB. So I have the energy due to the electric field, the energy due to the magnetic field. Now what we're going to do is we have a total amount of energy. And that total amount of energy will be equal to UB and UE, the sum of those two. And it's going to transfer back and forth. In fact, this circuit will transfer that energy back and forth forever, assuming there's no resistance. So this is what we would call an undamped circuit. It's never going to stop oscillating. Let's just sort of draw the figure of what happens here. We start out with our LC circuit. All right, it looks like this. Initially, I have charge on the capacitor. So let's say I have 4 positive charges and 4 negative charges here. So we'll just say that this is all of the charge. I have maximum Q. And because my energy is given by Q squared over C, I also have maximum UE. So the maximum energy is given in the capacitor. Now, over here, I have no current because all of my charge is sitting on the capacitor. It's not doing anything, but soon it's going to start discharging. But right now, at this moment in time, I have no current, and that means that over here, the energy is equal to 0 because I have no current. All right. So all the energy over here is in electric field energy. Now, as soon as this capacitor starts discharging, I get a little change. So now let's say I just have 4 charges. That means some of my charges have gone out. So I have a current that is not equal to 0, that's bigger than 0. This current is going to start out big and decrease. We've already seen that with capacitor circuits. So this current, actually, no, I'm not going to say that. So our current here is bigger than 0. That means that I have an energy here due to the electric field, and I also have an energy here due to the magnetic field. Now there is a point where UE is equal to UB. Always remembering that UL plus UB has to equal a constant value because of our conservation of energy. We're dealing with conservative forces here with the charges, and so our conservation of energy holds. So whatever our total energy is always going to remain the same. All right, so here UE plus UV is equal to some constant value, and that carries through all the way, that the sum of those energies will always remain the same. All right, now at some point, my current here is bigger than 0, and my current is also increasing. Our current is increasing here. This is a little tricky. The current is being pushed by this capacitor. What is it doing? Is it decreasing or increasing with time? The current is being pushed by the capacitor. As charges go away from the capacitor, what's going to happen to the current? Decreasing or decreasing? What do y'all think? Okay, this current is going to be decreasing with time, which means that the inductor is going to do what? Increase, right. So as the current in the capacitor decreases, or as the current that the capacitor pushes, if you will, it provides voltage to, then the capacitive inductor is going to try to fill in the blanks, basically, and try to increase the current. So the effect is that eventually I'll get a maximum current. All right, so my next step here is I have no charge at all. So here Q is equal to 0. All of my charge is out. Here I have maximum current. And when I have maximum current, I have maximum energy tied up in my inductor. What is my energy in my capacitor? It's 0, right? So here UE is equal to 0. So I start out with all of my energy in my capacitor, no energy in my inductor. As I go through this process, this circuit, as it oscillates back and forth, I get some energy in my electric field and some energy in my magnetic field, and then I get no energy in my electric field and some energy in my magnetic field. When I have max UV because the current is at its maximum. So my magnetic field is also at its maximum. Remember, we saw this last time, that our magnetic field due to a solenoid was mu naught I over 2 pi r. As I gets big, my magnetic field increases, and so my energy is going to increase.
Like I get why the current increased there, but why did you say at the second one that the current was going to decrease?
I misspoke. The current, I was talking about the current coming off the capacitor. That's why I backtracked a little bit.
Okay.
So here my current is actually increasing. It's because this capacitor, as it's discharging, remember when doing RC circuits, just a capacitor discharging through a resistor, it causes a decreasing current. But we don't have a resistor in this case. Actually, the effect here is that because of our inductor, our current is going to be increasing here. Okay? Okay, so here I have maximum current, and then I start going back the other direction. So then my next step, and it will continue back through the cycle, is that I'll have my capacitor, my inductor. Now my charges are going to be switched, so negative charges here, positive charges here. Notice that up here, they're switched, right? Because now my charges are going to switch plates, switch polarities. And just like we had in this scenario, my energy due to the electric field will equal to the energy due to the magnetic field. All right, it's also going to be that my current is going to switch directions. Just because of the way we talk about conventional current is this flow of positive charges. Okay? Now we can talk about this in terms of, or let's actually draw what these plots look like. So if I draw a graph of, say, Q and VC, that's the voltage across the capacitor. Remember, these are related to one another. Q is equal to CV for a capacitor. So if I draw a graph of this, at point A, I have maximum charge. So at point A, I'm going to be right here, and my charge is going to decrease. It'll look like that. So this is point A. Right here, we'll call this B. We'll call this C. So this is point C right here. And then this is point, we'll call this D. This is point D. So just looking at, say, the charge on this plate, I have an initial positive charge that's maximum. Then here I have 0 charge because all the charges left the capacitor. And then here, actually, that's not point D. That is going to be, point D will be sort of in between. So my point D will be like right here. I can draw point E. Point E is going to be where I get my maximum charge on my capacitor and no current in the circuit, so we'll call that point E. Okay? That LC circuit is going to go through this oscillation over and over and over again. In fact, as I said, if there's no resistance in the circuit, a resistance will add a damping factor. If there's no resistance, this will go on forever. All right? It will just continually change energy back and forth. You can think about this in terms of a spring. May I go down from here? I might ask you some questions about this on the test and the free response. So I might just, give you a figure that looks something like this and ask you to describe to me the energy at particular points in either the magnetic field or the electric field. So be able to describe what happens in this LC circuit as it oscillates back and forth between the energy of the magnetic field and the energy of the electric field. And then also be able to describe what happens to the current. So for example, when this is at its maximum, that's a maximum current. When this is at its maximum, I have zero current. Because in order to have the maximum electric field energy, I have to have all my charges onto this capacitor. And if all my charges are on this capacitor, then I cannot have any current because there aren't any charges out in the circuit. They're all on the capacitor. Okay, so I often use the analogy of a spring to think about this. So with LC circuits, you can very much think of them as an oscillating mass on a spring. If we have our initial stage where we have all of our charges on the capacitor, which has more energy here, the inductor or the capacitor? The capacitor, right? The capacitor has all the charges on it, so all that energy is wrapped up in the electric field, which is in the capacitor. So UE is at its max. We can think about this as a spring, mass on a spring, where we'll call this X equals 0. So it's like all the potential energy of this spring is at its very maximum. And you can sort of think about this as being potential energy of the spring, because there's no current flowing right now. In a similar way, the spring is not moving. So it's like all the energy is in potential energy of this electric field. All right, now, if we have, skipping ahead a couple steps, where all the current is now to where we have no charges here, Q is equal to 0, that means that my current is at what value? Is it at 0, somewhere in between 0 and maximum, or is that its maximum? Let's do it as a clicker question. So here, in this scenario, is my current, is it maximum? Is it 0, or is it in between somewhere? Is the current 0, maximum, 0, or is it in between? Did I tell you all my Batman joke? Oh, you're gonna like it. It's okay. We'll stop at 22 or 25. We'll go into 25. All right. Okay, very good. Our current is at its maximum. Look, all the charge is gone from the capacitor. That means all of that charge is out in that circuit somewhere, doing what it does and running a current. Listen, what did Batman say to Robin just before they got into the car?
What?
Get her in the car. Do y'all get it? It's sort of like that, why did the chicken cross the road to get to the other side? It's funny just because, because it's funny. Get your car. My family didn't get it either. But my 102 class, they got it. They thought it was really funny. But maybe they were just laughing at me, not with the joke. They just thought, gosh, what an idiot. Okay, so anyway, here our current is at its maximum. Also, UE is equal to 0. UB is equal to its maximum. So here we can think about our spring when it's at the equilibrium position. Remember, when it's at the equilibrium position, my kinetic energy was equal to its max, and my potential energy was equal to 0 there. So in a similar way, you can think about this, that the current is sort of akin to our kinetic energy, and the current here is at its maximum value, giving us the energy in the magnetic field to be at its maximum. And then we can go back in the other direction, where we switched the polarity of our capacitor. So now we have negative, 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 positive, positive, positive. That means that the current, or excuse me, that there's no current, excuse me, no current. And if we think about this in terms of a spring, then it means that it's now compressed in this other direction, where our equilibrium position is right here. All right, no kinetic energy, and my potential energy now is at its maximum, but it's in the other direction. All right. So you can think about this in this way, that I'm really just switching energy back and forth, back and forth, back and forth between the capacitor and the inductor, going from magnetic energy to electric field energy. So I can do the loop rule for this. The potential across the capacitor plus the potential across the inductor has to equal to 0. That's just the loop rule that we saw in chapter 4. The potential across the capacitor, remember Q is equal to CV, so V is equal to Q over C. The potential across the inductor is L di dt. We already saw that. That's sort of a variation of Faraday's law, that my potential across the inductor is L di dt, or the negative of that, and then that's going to equal to 0. Again, this is a first order differential equation. I can redefine and say that I is equal to dq dt, because that's how we define current. It's the derivative of the charge with respect to time, how much charge passes a point in a given time. And so I can rewrite this and say that it's, I'm going to give myself a lowercase q here to keep them all straight, minus L d squared q dt squared, that's equal to 0. This is a differential equation. What type of differential equation is it? Remember, last time we were dealing with first order equations. What's this one, you think? Second order. I know a lot of you haven't seen differential equations, but you will next year or two. So we just want to find a solution to this such that if I have a function and I take the derivative of it twice, I want it to be such that it's the negative of what it began as. See, because I'm going to have that function, I'm going to put it here, and then over here I'm going to take the derivative of that function twice, and I want to get back to the negative of what I had before. So not Cody or Casey or whoever, but what function is that going to be? Right. What is a function if I take a derivative of it twice? Well, I get back to that original function, but the negative of it.
It's a trig function.
It's a trig function, right? It's either sine or cosine, right? So if I take the derivative of those twice, then I get back to the negative of what it was. So I'm going to tell you what the solution is, and then I'll just show you how it works out. The solution of this second order differential equation, second order, ODE they call it, second order, oh wait, no, that's not, O is for ordinary, isn't it? Okay, ordinary differential equation. It's a second order differential equation. So my solution to this is going to be that Q is equal to Q cosine of omega t. Omega is going to be our angular frequency, and omega is going to equal to, I'll show you, square root of 1 over LC. So this is the solution. This isn't the one I'm going to have you do for a take-home. The one I'm going to do for a take-home is a little more complicated, but let me show you how this one works. So if I start with I'm going to start with this. I'm going to rewrite it just a little bit. I'm going to have d squared q dt squared. I want to show that this is equal to minus 1 over LC times q. So I'm just going to plug in this function here, take the derivative of it twice, plug in this function here. I want to show that these two are equal to one another. I just rewrote this a little bit from here, did a little algebra to get it in this function, in this form of d squared dt squared is equal to whatever it is. It happens to be minus 1 over LC times q. All right, so let's do first ddt squared of q cosine omega t. The q can come out. If I take the derivative with it, I'll take the q out, ddt. Take the first derivative of that. The derivative of cosine is what? Is negative sine, so it's negative, mix up a little space here, negative sine omega t. But when I have this omega t here, I also have to take the derivative of this. This goes back to your chain rule, right? If you have the sine of u, the derivative of that is going to be the derivative of this times the derivative of the trigonometric function. So I'm also going to have an omega term out here because the derivative of omega t with respect to t is just omega. All right, so now I'm going to have q omega. Taking the derivative now of this whole thing, the derivative of negative sine omega t is going to be omega negative cosine omega t. Where I just took the derivative of sine, that's cosine, kept the negative, took the derivative of this term, omega t, it's going to be omega, and I get that solution. So I can tidy this up a little bit. I get q omega squared, negative q omega squared, times the cosine of omega t. All right, that's just this side. And now I want to show that that's equal to the right-hand side. So I'm going to have negative 1 over LC times q, which is q cosine omega t. That's just the solution that I've told you. That is the solution of that equation. Now I can show that this minus this 1 over LC, based on our definition of omega here, is equal to omega squared. That omega squared is equal to 1 over LC. So I get minus q omega squared cosine omega t. All right, so that does show that this is the same as this. So that is an appropriate solution for this differential equation. The one that you're going to be doing for your test involves both an exponential and a trigonometric function. So it's going to be a little bit different from both of these that we've done so far. If you have trouble with it, you can come see me. I can help you with it. Or you can also you can look online. You can probably find help there as well. This sit okay with y'all? Not going to have to do this on the test, but I will want you to do it for a take-home. It might be worth a little bit more than we've usually done, maybe more like 15 points. Is that okay? All right. Let's move on then. Let's do an example. You have some in your homework like this. With an LC circuit, you should be able to calculate the current at any time, be able to and also be able to calculate the energy at any time. If you know the current, then you can figure out what is the energy in that inductor. So let's consider this LC circuit. I have a capacitor, I have an inductor. My capacitor is 1.5 microfarads, and my inductor is 12 millihenries. Make sure you know your metric prefixes, folks, because they'll come up here. Just to remind you, the big ones that we'll be using are micro, 10 to the minus 6, milli 10 to the minus 3. So those might be the only ones that we'll be using. Let me think. What are we doing in this test? We have I think that might be the only ones you encounter. Yeah, just make sure you remember those, okay? Or make sure that you're quick at using it. Now, this doesn't really make any sense. I can't have any current unless this thing has been charged previously. So we'll consider that the capacitor has been charged by a 12-volt battery. All right, so you charge up this capacitor, you put all your charges onto it, so like what we had before, my positives all there, my negatives all there, and now I want to know, after you let that circuit go, after you let it start oscillating back and forth, after 1 second of that, what is going to be the current in that? All right, I can I first want to know what is the maximum current. All right, the maximum current occurs when UB is at its maximum. All right, because as we know, UB is equal to 1/2 Li squared. That's our maximum magnetic field, our maximum energy. And whenever that is at its maximum, then this is at its maximum. So if I want to know the maximum current, I need to find out what is that maximum energy. Well, how do I find out what is this maximum energy right here? What is the maximum energy wrapped up in the magnetic field? And all I really know is the charge on the capacitor. I know the capacitance, and I know the voltage, so I can figure out what is the charge on the capacitor. Any thoughts? Can I figure out the energy on the capacitor? I mean, I can. Can you figure out the energy on the capacitor? We did that before. If we know the charge or we know the capacitance, yes, we can find the energy on the capacitor. If I find the energy on the capacitor, that's the same as the maximum energy in the inductor. Because that energy switches back and forth, back and forth, back and forth. So if I find the energy on the capacitor, then that will be UB at its maximum. So UB max is going to equal to UE max. Whatever the maximum energy on that capacitor will be the maximum energy in the inductor. So I can say 1/2 Li squared is equal to 1/2 Q squared over C. Again, this equation is in your chapter 4 equations. And then I solve for I. I can get rid of my i's, my 1/2s rather. So I is going to be Q squared over LC. The square root of that. That's going to be 1.5 times 10 to the minus 6 farads. So you convert it to SI units times 12 volts. Square that. Divided by LC, which is 1.5. Oh, I'm sorry. 12 times 10 to the minus 3 henries times 1.5 times 10 to the minus 6. Take the square root of all that, and I get 0.13 amps. All right, so that is the maximum current. I could also use that to figure out what is the maximum energy in the magnetic field if I asked, but you could do that. All right. I also want you to be able to find out the current at any particular time. So if I go back to my solution for that for the current, my I, I'm sorry, I didn't show you this, I don't think. So my solution here is going to be Q is equal to Q cosine of omega t. Right, that is my solution for the charge. If I want to know the current at a particular time, what do I need to do to this function? This is on your equation sheet, but what do I need to do? I have charge. If I want to know current, what do I have to do to charge? How is current related to charge? I is equal to what in terms of charge? None of this. What? Q over t, right. And not just any Q over t, but the derivative of Q with respect to t, dQ over dt. So I need to take the derivative of this function. So if I want to know my current, this I is equal to dQ dt. That's equal to I max sine of omega t. Yeah. All right, so this is my function for the current at any particular time. If I look back at my equation sheet, let me just sort of orient you here. It's right here for an LC circuit. I tried to lay it out very clearly for y'all because there are a ton of equations here that my current is equal to I max over sine omega t. Those things regarding the energies are back up. You're ready to print out those equation sheets. Are they in your book?
Yeah.
Oh, awesome. Yeah, so they're in the back of your book. Okay. All right, so then if I want to know my current at any particular time, I know my I max is 0.13 amps times the sine of omega t. Omega, remember we said was it square root of 1 over LC, I think? Times the sine of the square root of 1 over LC. We know L is this value, C is this value, times omega t, or times t. I think I want to know 1 second. Yeah, at t equal 1 second. And then I calculate what that value is. Be careful here. If you make this mistake on the exam, I won't count off maybe a half a point or so, but this needs to be in radians. All right, so on this test, I'll try to remind you before you go into the test that you'll need to put your answer in as radians. Okay? Just you'll need to change your mode before. If you forget that or whatever, I'll just count off like a half a point. Maybe not even that. I understand it's just a mistake. Okay? Y'all clear with me? Remember, this term is going to go between 0 and 1. So our maximum here is always going to be 0.13. So at any other time, it'll be some value less than that. Does anybody have a value on that? Are y'all doing it? Here, I'll do it too. Just make sure we're on the same page. Oh, actually, I'm just going to leave it at that. If somebody gets a value, let me know. Okay, let's look at damp oscillations. Can I go down from here? Damp oscillations are a little bit different because the LC circuit loses no energy. That's because we assume that it has no resistance. That's not really true for any circuit because any circuit has resistance in the wires and in all the various components. Well, a capacitor doesn't have any resistance, but like an inductor definitely does have resistance. So a true LC circuit doesn't really exist. You can get an LC circuit that will oscillate for a really, really long time, but it will eventually damp out so that it loses its energy. Because if the circuit has a resistance, it will dissipate energy. All right, so we're going to look at the total stored energy. The total stored energy, as we've already seen, is the inductor, UB, plus the capacitor, UE, the energy stored in the magnetic field, the energy stored in the electric field. And this is equal to Li squared over 2, or 1/2 Li squared, plus Q squared over 2C. It's just like what we had before. It's just the energy stored in those different components. The energy stored in the inductor, the energy stored in the capacitor. Now, in an LRC circuit, I have a capacitor, I have an inductor, and I have a resistor. I have an I have a C, L, R. That's why I call it an LRC circuit, because it has those three components. It doesn't yet have a battery, any kind of power supply. We're going to get into that on Monday. But in an LRC circuit, I have this resistor. So what that resistor does is it dissipates energy. So while the total stored energy is this, it's going to lose energy at a particular rate. And the rate that it's going to lose energy, du dt, is going to be minus I squared R. We've been using capital I. I'll use capital I here. Minus I squared times R. A lot of times in books, they'll use a lowercase I for these things, but we'll use capital I for this sort of thing. Okay? So this is the total energy, and this is the rate at which you lose energy. So what it's going to look like, if I look at the total change in energy, it'll look like this. It'll be du dt is equal to Li di dt. That's the rate at which I change energy in the inductor, plus Q over C this is my capacitor, dq dt, this is all going to equal to minus I squared R. The rate at which I change energy is going to be this plus this, and then that'll equal to the rate that I lose energy over there. All right, I can write this out as a differential equation, and then I'll give you the solution, and then this is the one that I want you to do for the take-home. So it's going to look like this. First I'll recognize that I can write this di dt as d squared dt squared, d squared q dt squared. And so now I can rewrite this equation. It'll look like this. I'll have L dq dt d squared q dt squared. What I've done there is my current here is just the derivative of charge with respect to time, plus R, bringing this part over here, R times dq dt dq dt. All right, because I have I squared, this negative becomes a positive when it comes over, plus Q over C times dq dt. This is all equal to 0. I wrote it like this so that we can get rid of one of these dq dt's because I have it in all three terms and I can just cancel those out. So this is our differential equation, second order differential equation. Can rewrite it just a little bit. Just rewriting it, getting rid of that d squared q that's equal to 0. Okay, I'm going to give you the solution, and for the test, I want you to show me that this solution is correct, that when you plug these back in, that you get that this solution is correct. And the solution looks like this, that Q is equal to Q times e to the minus RT over 2L times the cosine of omega prime t plus a phase constant, which we'll get into later, phi. And here we're going to define omega prime as the square root of omega squared minus r over 2L squared. And omega is still what we had before. It's the square root of 1 over LC. Listen, the graph of what this is going to look like, I'm coming back to it. So the graph of what our function is going to look like, because I have this cosine function, it's going to oscillate back and forth. Because I have this exponential function, it's going to damp. So my function here will look something like this. I'll have a cosine function that's superimposed on an exponential function. So it'll look something like this. It's a damped oscillating circuit. It's not an uncommon thing to find in nature that you have something that oscillates and at the same time is being damped. I have two things here. I have the oscillating function here, and then I have the damping function here. In fact, if you go to PChem, you'll see this again, and if you go into grad school, you'll see it certainly in engineering. Okay, but it's a damped oscillating function. What I want you to do is take this function, consider what omega prime and omega are, and plug it back into here and show that it is correct. Let's see, I think you can just leave off phase constant. I'm pretty sure that that's the case, that you can just leave this off when you're considering that. But it will, yes, you can do that. You can leave off that phase constant, but I'm gonna include it here because it'll become important later. I think y'all can do that. It's really just derivatives that you're doing, but yes, I know that you can do that. If you need help, though, please come see me with that. You'll just turn that in. We have all week next week, so you turn it in on the day of the exam. And let's count at 15 points. It's not a trivial thing to do that. You can probably find the solution, but I want to see, all the steps laid out very clearly for you to get full credit. Is that okay, y'all? No, it's sleepy. Yes. I know this is a little dry, but it is so important that you at least get exposed to this right now. All right, I'll see y'all later. Y'all have a good weekend. We're gonna hold on just a second. Let me. So what I'm planning right now is I'm pretty sure we're going to finish this up on Monday. We might have a little bit left, but probably not enough to warrant the whole class. I might do it as a screencast, a 10-minute screencast or so if I can't finish it. And then if you have any questions about it on Friday, we can talk about that. It's just transformative, possibly, we'll do that. And they're fairly straightforward. We've already talked about them some. So I'm planning a class on Monday, but then not on Wednesday if there's no objections. I'll be around, of course, so if you feel like you need extra help, I'll be here, so you can come into my office and we'll, either there's 2 or 3 of you will just come in here and we'll all sit in our group and talk about stuff, okay? So if you feel like you need extra help, that's a good time to come Wednesday morning. But as always, I'm here, that's my job to help you, so if you need help otherwise, we can set it up at different times. All right, folks, we're almost done. Y'all have a good day, okay? Have a good weekend. Crawfish day today.